In this video, we're going to see when and how we can use two sample tests for means when we have paired samples. And in this video, we're going to use data pile foundations. So far, we've been working with independent samples for two sample tests for differences in means, population means. All right, so for example, we were talking about the sample of female students versus male students. And as you can see, there's no person, there's no one that can belong to both groups, to both samples, right? So these two samples will have, when we're talking about independent samples, the members in each samples are gonna be completely different from the other group. Whereas independent samples or paired samples, we can actually pair one number at one sample to another number at another sample. Actually, in a lot of cases, in the cases that we're gonna be working with, in paired samples, we have the same, exactly the same members in both samples. So we have, and then we have different numbers belonging to the same people or same objects, right? One actually way to identify whether we're going to use paired sample t-test or independent sample t-test is that one way that we can identify that would be by looking at the number of items in a sample. And as you can see here, both samples have the same number of members, and you can actually pair one by one the observations at each sample. You can pair them one by one. So if I go to the next slide, here we have two examples. So when we want to compare Walmart versus Target in terms of the unit price of the item that they charge, basically the price that they charge. It's better if you want to make a fair comparison. It's definitely fairer. It's definitely better if you can pick the same items. Pick the same items and then record the price at Walmart and Target, and then you will have a much fairer comparison, right? So here it's better if you can pair. Actually, in any case that you can imagine, it's always best if you can do a paired sample analysis. But when you're comparing females versus males, it's impossible to do a paired test. So in those cases, when paired is not possible, the only choice that we have is to go with independent samples. But whenever possible, it's always fairer. It's always better if you do a paired sample, two sample test. All right. The second example is when you have actually a change in system, and when you want to study the effect of that change in the performance of people, in the performance of the worker in this case. So a fair way to do this analysis is to pick a sample of workers and then see how they've done their work before implementing that change and after implementing that change, basically, whatever the change is, right? So before and after recording of the data, and then comparing these before after type of data. So this type of test, paired sample test, are actually also called before after analysis. And that's why, again, the sample is the same people, the same group of people are gonna be at both samples, but then the numbers, the first sample is gonna be about their performance, whatever it is, before the change actually is implemented before the new system is implemented. And then second set is the data actually, the performance, the variable after the system is implemented, after the change is implemented, all right? So whenever we have paired samples, we need to use a different type of test. It's called in Excel t-test paired two sample for means, right? So the difference here, before we use this one, two sample, t-test two sample assuming unequal variances. And now whenever we have paired samples, we're going to use t-test paired two sample for means. We're not going to actually worry about the test statistic and the details of the formula, right? We're going to use the t-test paired two sample for means tool in Excel for performing this type of test. All right. And then the hypothesis is slightly different from what we've been working with. Here, we want to see if the difference between each actually observation, each sample member before and after, if you take the difference between before and after for each member and have that actually as a new variable, the difference between before and after, and then we are now testing to see if there is a meaningful difference, if there is any meaningful difference between before and after, right? Before variable 1 and variable 2. So here we have one example. We have an foundation engineering type of project. The engineers here are estimating. They're actually bidding based on an estimate. So they're actually doing the research and try to come up with the best estimate that they can. And then they use this estimate to bid on the project. For those projects that they have won, they can actually see the actual pile lengths, the lengths of the piles, the actual length, and then they can compare it with the estimates. So that way they can see their performance, how they've done in terms of the estimation of the length of the pile. So now we want to see if the estimation, actually, if the bid information or the estimation basically was poor or not. So I'm going to open the data file here. So here I have the pile foundation data file, and I have the estimated values for the pile length, and I have the actual values, all right? So now, and then each row belongs to each auction. And as you can see, for each auction, for each bid, we have both estimated value and actual value. So this would tell us that, so there are two things here. So we have the same number of observations in each sample. Estimated we have 314 observations. Sorry, I think it's less. Yes, it's 310 observations in estimated column and 310 again in the actual. So same number of same size samples at both sides. And also for each number at estimated column, I can pair it with another number at the actual column. So for each, there is a one-to-one relationship. These two samples are dependent. I can find a one-to-one relationship between each number from this column to another number at this column, which is in this case, I have them in the same row actually. So this would be a case of paired sample. So what I'm trying to do, guys, I'm trying to see if estimated the difference, which is whatever you actually want to put first, doesn't really matter. In this specific case, we're gonna perform a two-tailed type of test. So it really doesn't matter, but I'm gonna go with the estimated first, estimated minus actual. So my estimation is 8 foot short, and then I just drag it down. So now I have 310, 311 actually differences, all right? So my objective now is to see if the population mean of these differences is equal to 0 or not. So that's what I want to test. And as you can see, now I have one column that I want to test. So this indeed is a one sample. I mean, I understand that we're using two sample, but then at the end, we're just looking at the differences, one-to-one difference. And I have a new variable, which is called a difference column, difference, right? So now I want to test to see if the average or the mean of population mean of this difference column is equal to 0 or not, right? So that's what I want to test. So null hypothesis, if the average, population mean of difference, and then instead of difference, I can type estimated minus actual. Estimated minus actual. And I'm going to conduct a two-tailed type of test. So equal and then not equal. So that's the hypothesis set. The next thing that I'm gonna do, I'm gonna determine the level of significance. And I'm gonna set it to 5% as our default value. All right, so alpha. All right, so let's go ahead and use the t-test for the mean when we have paired samples. So I'm gonna go to data tab, data analysis, t-test paired two sample for means. So this is what I'm gonna use. So variable one range, it's gonna be the estimated value, estimated column. Variable two range, this one is gonna be the actual number. Actual number, C5 to C315. I did not use the labels, but let me just change it to B4 and this one to C4. That way I can check the labels because in row 4, I have, as you can see here, now estimated is included. So I check label, so it's there. Hypothesized mean difference is this value, the value that I'm testing. So we can, we don't have to always put 0. We can actually, similar to the t-test two sample for assuming unequal variances that we did, we can set the hypothesized mean difference. So here, we're gonna just put 0. Output range, we just put it at the same sheet. All right. Okay, again, the only thing, this is a two-tailed type of test, so the only thing that we need at the end would be p-value two-tailed, p-value two-tailed. Excel, again, similar to what we had before in the other t-test two-sample, assuming unequal variances, we also have a one-tailed, but if our test right now is a two-tailed type of test, so we just look at this one. But for one tail, Excel just gives us one number. So this is up to us to figure out what type of p-value this one is. And then again, the difference, the way we can identify that is by just looking at the test statistic. If the test statistic is negative, this would be p-value lower tailed. P-value lower tailed, right? If this was positive, then this would have been p-value upper tailed. But now this is p-value lower tailed. If we wanted to have p-value upper tailed, that would be simply 1 minus p-value lower tailed. That's something that it's good to know. Just add some. It's almost 1, yes, almost 1. This is 0, right? All right, so now writing the conclusion, of course, the p-value two-tailed is less than 5%. And this number, it's actually, you see this E minus 23, this is the scientific type of display in Excel, scientific notation, actually. When you want to display a number that is so small, so this actually implies that there is 23 after the point, but it just saves some space, right? So I'm gonna say since p-value two-tailed is less than alpha, and alpha we just assumed is 5%, we can conclude that, we can conclude with 95% confidence that, so we're gonna reject the null hypothesis. All right, so we, since p-value two-tailed is less than alpha, we can reject the null hypothesis and conclude with 95% confidence that the difference, there is actually a meaningful difference between estimated and actual values. All right, so this is what we are concluding. So if we just take the alternative, that would mean that there is a meaningful difference between, or the difference is not equal to 0. I conclude with 95% confidence that the difference between, or that there is a meaningful difference between estimated and actual values, actual lengths files.